presentation. So thank you, Lorenzo, and thank you all for attending today. Is it okay for the sound like this? Yeah. So maybe just some words to introduce a bit myself before beginning. I'm going to present today a work that I did during my PhD, which was between 2017 and 2020 in France, in Seminario in Grenoble. And after my PhD, I've been working during almost 2 years outside academia in the French Ministry of Environment on a big project called Green Data for Health. And now I'm going back to academia in Italy, and I will be joining in a few weeks the Human Technopole Center in Milano. So today I'm going to present this meet-in-the-middle approach using DNA methylation to inform the exposome exploration. So this will be about omics epidemiology and a bit of causality. So after a brief introduction, I will present the approach that we developed, the meet-in-the-middle, and then I will firstly present an applied study where we use this approach to relate the exposome to child body mass index in ELIX data. And then I will present another work where we validate with more theory and lots of simulation this approach. So let's begin with the exposome concept. As you may know, the exposome concept encompasses all the exposure to which individuals are exposed from the conception, all the environmental factors. In a word, it's all non-genomic factors to which you are exposed and that could maybe potentially have an effect on your health. The concept was introduced in 2005 by Wild, and for now more than 10 years, there have been many epidemiological studies which use exposome cohorts. For example, in this picture, you can see the different families of exposure which were measured in the ELIX exposome project, and you can see that we have lots of different families, but mostly chemicals and physical contaminants. Chemicals, for example, phthalates, phenols, etc. And you can see also that one of the big challenges of the exposome is the correlation structure within all these variables. So why should we use the exposome in environmental epidemiology? As almost always, the aim is to find and estimate causal association between exposures and health outcome. You know that traditionally in environmental epidemiology, we used the classical single exposure model. We have one environmental model, one environmental factor, sorry. We suspect an effect on a health outcome, so we can do a regression adjusted for the relevant factor. Now, with the exposome, with the exposome data from exposome cohorts, we are able to consider lots of exposures at the same time. There are many promises, in fact, in using exposome data in epidemiology. The first big advantage is that it allows to, in fact, limit selective reporting and deal with publication bias. When you test 100 exposures and you report all your exposure, it's a way to deal with publication bias. The other big advantage is that with exposome study, we can explicite and possibly avoid the question of multiple comparison. As you know, multiple comparison is that when you do a lot of tests, you have a chance to see significant associations by chance, so multiple comparison. Thirdly, within an exposome study, we are now able to take into account confounding by co-exposures. And I just showed before the correlation structure within the exposome. It's really important to take into account this possible confounding. And lastly, at least theoretically, because for the moment it's not really largely done, within an exposome study, we could be able to consider mixtures of chemicals and synergistic or additive effects. Now, how could we analyze exposome data? It's fine. The basic method is just the translation of the univariate regression to multiple factor. It's the XWAS, or exposome-wide association study, and basically it's just multiple univariate regression corrected for multiple testing. The first one was done by Patel in 2010, and since that, there have been many more. But there are lots of methodological challenges. As I said before, the question of multiple comparison, there are lots of wonderful work about how we can correct for this. But another big problem is that the fact is that when you have lots of correlation within exposure, and when you have small cohorts, because in fact it's difficult to measure lots of exposure on lots of people. So when you have big correlation on small cohorts, in the XWAS you have many false positive findings, what we call a high FDP, or false discovery proportion. You can see it in this picture, which comes from a simulation done in 2016, where different methods to select true predictors were tested in an realistic exposome setting. So two metrics were used to assess the performance of the different method: the sensitivity and the FDP for the exposure proportion, which is a measure of specificity. So I don't know, do you see my mouse? Yes. So the idea is to be in this square to have a high sensitivity and a low FDP. This is what we expect for a good method. And you can see that the little squares for the XWAS are all here. This means that they have good sensitivity, they are able to detect the exposure, but you have a terrifying FDP. 90% of FDP, it means that you can't at all trust your result impact. And there are also methods, for example, the best one here is DSA for the distance repetition addition algorithm, which are better, but they have still a big FDP. So in this simulation, there are no statistical methods which show both high sensitivity and low FDP in a realistic exposome settings. So what could be the solution? Possible solution, which has been explored for some years now, is to try to apply dimension reduction methods to the exposome. But the important point here is that we should use the dimension reduction method, which could be interpretable, because the aim is always to select exposure with biological meanings and on which we could act from a public point of view. So we need to do selection of variables and to have a dimension reduction which is interpretable. So this can be done statistically, and there are many wonderful people working on many wonderful methods. And this can also be done using additional biological information. So what can be the source of biological information that we can use? An important one is the intermediate layers laying between the exposome and the health, which are a wonderful source of information. Between the exposome and the health, you have all these omic layers, this biological layer, for example, the methylome, the transcriptome, and the proteome, where we can find biomarkers of effect of biomarkers of exposure. So we know that there are lots of information in this intermediate layer. Specifically for the methylation, DNA methylation is the addition of a methyl group in a cytosine guanine complex on a CPD site on a DNA chain, and we know it's essential to control DNA construction and thus all the cell functioning, cell differentiation, phenotype, functioning of the organ. And we know that methylation is affected by environmental factors, and we also know that the methylome could also possibly mediate some environmental effects on health. So this is a possible source of additional biological information that we could use to reduce the dimension of the exposome. So the aim of this work is to tackle the challenges of high FDP and low sensitivity in exposome studies with a new approach using a priori biological information from the DNA methylation layer. So what we've done is to propose an adaptation of a method using epimery, which is a meet-in-the-middle approach. And so this is the method that I'm going to present, our oriented meet-in-the-middle approach. So this is the proposed design. Here the aim is to use the methylome to select exposure likely to be relevantly associated with the outcome. In fact, it's to perform an informed dimension reduction of your exposome using the methylome data. And this is important. In this design, we do not use the methylome to try to find new knowledge about biological mechanism, about mediation by the methylome. We really just want to use the methylome to select relevant exposures. We do not care about the significance, the biological meaning of our methylome data. So I use the methylome to perform an informed dimension reduction of the exposure. To do this, it's just a simple design in 3 steps. The first step is to test the association between your methylome and your outcome. Is an XWAS type analysis, for example, so like an exposome wide, it's a methylome wide, you test all your association and you correct for multiple testing. And this allows to select a reduced methylome, which gathered all the CPGs which are associated with the outcome. Second step, it's to test the association between these CPGs and each exposure. And this is important because this is one of the differences with the traditional methylene needle. At this step, we adjust the test on the outcome. And in fact, this allows to select a reduced exposome, which is basically just all the exposures which are associated with at least one CPG associated with the outcome. So in a way, it's the exposure which are associated with relevant CPG for our outcome. And the last step is just to test the association between your reduced exposome and the outcome. So this is the oriented needle. For the implementation, first idea was to do ex-post type approach at all steps, a linear regression, collected from multiple testing, but we proposed two adaptations from the beginning. The first one is in order to deal with the high dimension of the methylome. In a way, it's a bit paradoxical to use high dimensional layer to reduce the dimension of an intermediate dimensional layer. We have this high dimension of the methylome. The idea here is because we do not care about the results on the methylome layer, it's possible to use a priori additional knowledge on the methylome preliminary before our meeting the middle. So we add a step 0, which is to preliminary select some CPGs relevant for our outcome according to the literature in epidemiology, in toxicology, and this kind of thing. So firstly, use knowledge, use information to reduce the size of the methylome. And second adaptation, which is more logical, we know that there are methods that are better than XWAS to test the association between the exposome and your outcome, and we could use them at the last step. For example, we could use the DSI algorithm. So this was our meeting the middle. And now I'm going to present a study that we have done in the ELIX course using this method to relate the exposome to child body mass index. So here the aim is to relate the exposome pregnancy and postnatal exposome to child body mass index by taking advantage of the methylome data. So we work on the ELIX LLF exposome project data, which is a big European exposome project, which is now continuing with the athletes, which Lorenzo's team is part of. And we work on we have the data from 6 different European cohorts, in total a bit less than 1,200 children. And our outcome was a standardized child body mass index, a measure of obesity and upper rates, measured between 6 and 9 years during the standardized clinical examination. Our exposure. We have the full exposome of ELIX, 216 exposures, assessed part of them by biomarkers in urine or blood, for example, the phenols, the salates, and the metals, and part of them by environmental models and questionnaire, by the way, for example, built contaminant, metallurgical data, air pollution. We have 2 exposure windows, one during the pregnancy of the mother, and one in childhood at the same time of the clinical examination of the measurement of BMI. Now coming to the methylome, we collected samples from child peripheral blood at the same time as the measurement of BMI, and the methylation was measured using methylation 450 linear bed shape. Data were normalized and filtered and corrected for batch effect. And as I said before, we chose to perform a preliminary dimensional reduction of the methylome using data from the literature. In fact, we use the CAGE database, which is a database of pathways, and we select pathways relevant for BMI using keywords. And then we select all the enhancer CPGs belonging to genes belonging to these pathways. And this allows us to dramatically decrease the size of our methylome, the dimension of our methylome, because at the beginning we have around 400,000 CPGs, and now we have a methylome restricted to 2,284 CPGs. So this was the data for the second statistical analysis, the oriented methylene needle approach that I just described, and we compared it to a classical exposome-wide test, an agnostic exposome-wide test, in fact, ignoring the methylome layer. We did the analysis on the whole exposome, and as I said before, we use multiple universe linear regression corrected for multiple comparisons using the Mendelian-Schberg procedures, and we adjust for the relevant covariates. We did many different sensitivity analyses. The most important one is this agnostic exposome-wide analysis, so ignoring the methylome. Here are the results. You have the different characteristics of the study population. We have a child BMI, which is around 17 kilograms per square meter, but you can see here that it varies across cohort, with the top are the Spain and French cohort, I think. Now coming to the results. So let's go step by step and look at the results of each step of the oriented methylome. As you remember, first step is to test the association between our methylome produced with the literature and the outcome. You can see here the results. You have on these plots, on the x-axis, the p-values, here the CPGs, and the black line is the significant threshold adjusted for multiple comparisons. And you can see that we have 62 CPGs from 33 different genes, which were selected with BMI. So this is our reduced methylome. Now, next step is to test the association between each exposures on each of these 62 CPGs. Here are the results. You can see that we have 4 exposures which are selected with at least 1 CPG related to BMI. So this is our reduced exposure consisting in 4 exposures, 1 pregnancy exposure, immunity level, and 3 postnatal exposures in levels in blood of copper, PFOS, and BPA. And interestingly, copper was associated with an important number of CPGs, 52. So this is it. We have done a dimensional reduction of the exposome using information from the methylome layer. Now we just have to test the association between this reduced exposome and the outcome. And this is the result. Among these 4 exposures, 2 are significantly associated with our outcome. A positive association for copper, which is associated with higher BMI, and a negative association with PFOS. So meet in the middle allows to point to this. Now you may ask, what if we did not use the methylome? What about the agnostic exposome-wide association study? Here are the results. First point, we have far more hits with the XWAS, but this was expected. As I said in the beginning, XWAS is known to have really bad FDP, to have lots of false positive. And one of the ideas behind Meet in the Middle was to try to reduce, to increase the specificity, to reduce the FDP. So we expected to have less hits. So, okay. Now there is another interesting point here. In fact, lots of the hits, not all, but lots of the hits of the XWAS are unexpected negative association of highly correlated PCBs and other lipophilic substances. And I say unexpected because there are some epidemiological and toxical studies which suggest, in fact, that there is an obesogenic effect of PCBs. So it was unexpected. What could be the explanation here? In fact, we have an hypothesis, which is maybe here, what we see is a phenomenon of reverse causality. In fact, when you have a higher BMI, you are bigger, you have more fat mass. And the lipophilic substances, for example, the PCB, are more stored in fat, and this could lead to decreased levels in blood. So here, a phenomenon of reverse causality. And remember, I said that the PCB in blood was measured at the same time as the clinical examination. So a good hypothesis here is reverse causality. Now let's sum up. For copper, in fact, the association is plausible. There are some toxicological and epidemiological studies that show an effect of copper on overweight, and there are even animal models in fish that suggest that this effect could be mediated by the methylome. So the plausible causal diagram for copper is this one, with an effect of the exposure on the outcome mediated by the CPGs, by the methylome. We found the hit both in Meet in the Middle and in classical XWAS. So if this diagram is true, we have a true positive for both Meet in the Middle and the XWAS. For the PCBs, the hypothesized tag is this one with reverse causality. And we did not find the hits with Meet in the Middle, but we found the hits with XWAS. So if this diagram is true, Meet in the Middle gave us a true negative, and classical XWAS gave us a false positive. So this applied study in Helix allowed to point an interesting association with copper, allowed to think about reverse causality, but it also allowed us to make some hypotheses about the behavior of our method. So 2 main hypotheses. The first one is maybe the Meet in the Middle allows to discard some of the association due to reverse causality. And the second one is that maybe in mediation situations, due to the reduction dimension, the Meet in the Middle allows to have a high specificity than XWAS. And to verify this hypothesis, we chose to do a simulation study, which also allowed us to systematically compare meat in the middle to other agnostic methods. So this is the second part of my presentation. I don't know if I have time. Yeah, I think so. Which is how we try to validate our meat in the middle approach with a big simulation. So let's begin with an overview of the method. It was the Monte Carlo simulation. And when you do Monte Carlo simulation, first thing is to define the causal structure you want to test. For example, one of the decks that I showed before. Then within the causal structure, you have to define scenarios, define the magnitude of the means, define the number of predictors, these kind of things. Then you have to generate a realistic structure for each of the layers according to your causal structure. You generate here 3 layers, exposome, methylation, outcome. And then you test your method. You know which are the true predictors. You run your method, and then you can assess if the XPath, for example, has found or not the true predictors. And then you repeat. And we simulated 100 offset by scenario, and we have something like 2,500, I think, scenarios. And this allowed us to estimate the method performance in different scenarios and under various causal structures. And again, we have the two same metrics, FDP for specificity and sensitivity. Here are the 5 causal structures considered, and today I will focus on the 3 most interesting, these 3 ones. So the first one, indirect effects. All the effect of the exposome is mediated by the methylome. Second one, no mediated effect, just a direct effect from the exposome to the outcome, and a direct effect from the methylome to the outcome. And last case, last structure, reverse causality structure. For structure, we bootstrap with data from EVIX to similar to holistic layers. We use only continuous variables, and we always assume linear effects. And as I said before, we simulate lots of various scenarios for interstate assumption and the number of true predictors. For the method that we tested 3 holistic methods. The XPath that we use in our applied study, LASSO, which is a well-known selection method, and DSA, for deletion substitution addition algorithm, which was the best method for an exposome setting according to the simulation of Lineage. First method, the basic anti-meat in the middle that I just showed for you, so no difference, 3 steps, XPath type analysis at all steps. Second one is a slight modification by retesting at the last step the XY by the DSA, which is known to perform better in this setting. And last method is a mediation analysis. Here we use the mediation analysis to select exposure. So in fact, the selected set of exposure are all the exposure for which we find a significant mediation effect. So it's like the middle, it's in 3 steps, the basic traditional mediation test. First step, test your association between your exposure and your outcome. So you select some exposure. Second step, you test the association between your exposures, the selected exposures and the potential mediator, here the methylome. And last step, you test the association between those variables from the methylome and the outcome. And because this is a mediation analysis, you have at this step to adjust on the exposure. So basic mediation analysis. So these 3 methods make use of the methylome. And we also add a control methods, and I explain it here because I will use it later. In fact, it's an XPath and a random subsample of exposures. Every time we run a meat in the middle and we obtain a reduced exposome, we also randomly draw a set of exposure of the same sign of the reduced exposome, and we apply an XPath on this. So it's a way to try to see if our reduced exposome is concentrated in true predictors or not. So it's really a control method, XPath on a random subsample. Let's go to the results, at least for this first structure. So indirect effect of the exposome and the outcome totally negated by the methylome. So let's go for some plots of results. So here you can see the performance of our meat in the middle implemented with XPath. What is important is here is the x-axis, the variability of the outcome explained by the exposome. And you have the R2 matrix here, FDP. In fact, we use 1 minus FDP and the sensitivity. So for both metrics, the higher the better. If for one, it's perfect. If you have one minus FDP of 1 and sensitivity of 1, it means that you found all the true predictors and no other variables. So you can see that when the variability of the outcome explained by the exposure, so when the effect is higher, the FDP is, the specificity is decreasing and the sensitivity is increasing. In fact, at the beginning, when the effect is low, mid and middle does not see anything, and after it's a bit like XY, it sees something, but there are lots of FDP. But the big question here is, was our dimension reduction useful, and is the mid in the middle more specific than our XYs? So here I compare the mid in the middle here on the right XYs, FDP each time, and you can see, for example, on the purple line, that the specificity is a bit better for mid in the middle. And compare the two purple lines. So yes, we find that mid in the middle is more specific than XYs. And interestingly, it's also more specific than mediation. So again, if you compare the purple line and the blue line, you can see that, yes, mid in the middle is more specific than mediation. So this is the first good point for mid in the middle. Now, to understand how mid in the middle is behave, the question is our radius exposome relevant? So for this, we use our control method, XPath at subsample. And we compare the sensitivity of the mid in the middle, so the sensitivity of an XPath on the radius exposome, and the sensitivity to an XPath on the random subsample of exposure. And you can see that the sensitivity is far better for mid in the XPath. So in fact, it means that our radius exposome is indeed concentrated in true predictors. So yes, with the methylome, in this causal structure, we were able to perform relevant dimension reduction of the exposure. And interestingly, you can see that we have exactly the same FDP, because the FDP within a fixed correlation structure, the FDP depends on the dimension. So what I know. So our radius exposome is relevant. Now, just some small words about the agnostic method. Unsurprisingly, DSA was the best method, and I won't detail, but it has the same kind of specificity than XWAS and LASSO, but it has a far better specificity. So it's better than LASSO, better than XWAS. So the best agnostic method is DSA, and this is consistent with the previous studies. Now, what is the best method? In fact, the best method is mid in the middle with the DSA implementation. Here we can compare the mid in the middle DSA with the mid in the middle XWAS, and you can see that when the variability of the outcome explained by the exposome is high, here you have a far better specificity for mid in the middle DSA on the same kind of sensitivity. So yes, mid in the middle is really better with DSAs than with XWAS. And you can see that it's also better than DSA, because when the variability of the outcome explained by the exposome is low, here we have a FDP which is non-1, so the specificity is lower from DSA than for mid in the DSA. So mid in the DSA is better, is the best method. It has both the advantages of mid in the middle XPath and the advantages of DSA. So best method, mid in the middle DSA. So for this first causal structure, mid in the middle seems to work well. Seems to be a good strategy. Now, what if we do not have any mediation? So second structure with a direct effect of the exposome on the methylome on the outcome. First question, does mediation, in this question without mediation, does a mediation test detect some predictors? Unsurprisingly, no. We have FDP of 1, 0, no hits. Okay. But for mid in the middle, it's slightly different. You can see that we have a FDP which is non-zero, and we have a sensitivity which is non-zero when both things are high, are strong. So, strangely, we have some hits for the mid in the middle. And to understand this, let's have a look at the reduced exposome. So again, I compare my mid in the middle XPath with my control method, and I can see again that the sensitivity is far better for mid in the middle XPath than for XPath on subsample. So these hits are not just here by chance. It means that really we are able to select some relevant exposure in our reduced exposure. Why? In fact, remember that at my second step of mid in the middle, when I test the association between the exposome and the methylome, I adjusted on the outcome. And you see on this diag Here, the outcome is the common consequences of exposome on methylome. So if you adjust on it, it's the causal inference theory, you create a selection bias. So a spurious association between the exposome and the methylome. So that explains why I have some relevant exposures that are included in my reduced exposome due to this adjustment on the outcome. Now, again, in this structure, the best diagnostic method is DSA. And the best method using the methylome is again the implementation with DSA, but it's of course methynyl DSA is less performance than DSA because we have only a few hits in this situation. So in this situation, in this causal structure without mediation, methanol is not a good choice, but at least it's wrong in a good way because it does not give some false positive. And interestingly, it could, in some case, still put relevant exposures in the reduced exposure. So not so bad. And last situation, reverse causality. So in this case, a perfect method would not detect anything because we have no causal link from the exposome to the outcome. But we still want to assess the performance of the method and to see how bad are the methods. So we have two new metrics, the number of hits on a perfect method will give 0. And we also assess the sensitivity to exposure influenced by Y. In fact, it's the same as sensitivity, but using as if the predicted exposure are predictors. So it's just to see if the method indeed selected the exposures that are predicted by the outcome or just random exposures. So let's begin with agnostic methods. Are agnostic methods prone to reverse causality? As expected, yes. When you test the association between A and B, you have no way to distinguish an effect from A to B and an effect from B to A. So yes, we found that agnostic methods are prone to reverse causality. We have some hits for the X-rays for DSA and for LASSO, and you can see with the sensitivity to exposure influenced by Y, by the outcome, that indeed the exposures selected are the exposures that are mainly the exposures that are predicted by the outcome. So here we observe the same behaviors as in the previous structure, as if predicted exposures were predictors, but this was totally expected. This is the same case for us. Now, what about meeting the middle? Good point for meeting the middle, we have no hits. So in this case, meeting the X-phase and meeting the DSA did not select any exposures. This allows a link to our previous applied study. Remember that in the applied study on hits, we have lots of hits that we suspected to be due to reverse causality in the X-phase that did not appear in the meeting the middle approach. So this is consistent. Before thinking about the reason behind that, let's have a look at the mediation. Mediation, contrary to meeting the middle, detects some hits. And you can see that the number of hits depends on the magnitude of the link between the outcome and the methylome. So let's have a discussion with the tag again. Remember that in a mediation analysis, when you test the association between the exposome and the methylome, you do not adjust on the outcome. So here the outcome acts as a compounder, so you detect a spurious association between the exposome and the outcome. And with our meeting the middle, at this step we adjust on the outcome, so no spurious association was detected. And that's what, in this case, we were able with the meeting the middle to get rid of the reverse causality association. So on these three structures that we simulated, meeting the middle seems to be a good option, even better in some cases than the agnostic methods. But what about all the other possible causal structures? We investigated by simulation only 5 structures, but there are 25 possible causal ones if you have all the combination between 3 variables. So what we did was a theoretical analysis of all the possible DAG. And for each DAG, at each step, we look for bias, if it was a negation, if it was meeting the middle, if it was just a basic association. And this allows to count the DAG in which each method is expected to behave correctly. And by behaving correctly, I mean if the exposure is non-causal, no detection, and if the exposure is causal, detection. Here you can see all the causal structure for which methylene middle is expected to behave correctly. On the left, all the true positive. The exposure is only detected by methylene middle, assuming perfect flow, of course. This is a theoretical analysis. And on the right, true negative, the exposure is not causal and is not detected. And among the true negative, you have these three structures for which a basic test of association, so an X was on any other method directly relating the exposure to the outcome, would erroneously detect the link, because this is some situation of reverse causality. And in fact, if we count the different causal structure, we can find that methylene middle is expected to behave correctly in more causal situations than mediation and then basic association test. And this is really important because this means that methylene middle is a bit more robust for the underlying causal assumption. And as you know, with all the high-dimensional layers that we now study in epidemiology, there are lots of complex links within a layer, and there may be lots of different causal structures that are present in the data, in the same data. We could have a situation of mediation for a single CPG, situation of reverse causality for another CPG, and this kind of thing. So it's a good thing to have methods which are robust for the underlying causal assumption. So let's conclude. And about the usefulness of our method and a bit more largely about how we could put the false positive problem in a larger causal framework. The first thing is that when you have reverse causality or mediation, yes, it could be useful, and in our case it was useful, to manipulate information from the methylome to remove some false positive hits. In the case of reverse causality, we remove some false positive hits which are linked to causality. Or in the case of mediation, we could remove some false positive hits which are just linked to the dimension of reduction. So this is a validation of our anti-methylene middle design. Now, in situation with a direct effect from the exposome to the outcome, not involving the intermediate figure. So, of course, methylene middle may not be efficient where some agnostic method may, but as I said before, methylene middle is wrong in a good way because in this case, it does not display some false positive hits. And the last conclusion from our simulation was about the implementation of methylene middle. So it was easier to compare to agnostic method to use the methylene middle XPAS than to compare to XPAS, but we found that a bit obviously, but it's better to use method with better performance as the last step. And methylene middle DSA overall provides very good performance in terms of balance between sensitivity and specificity in our realistic exposome data. And I didn't show it because it's only on some scenarios, but in some case, it was the method DSA even show increased sensitivity compared to agnostic approach. It means that our dimension reduction could, in certain situations, allow to increase sensitivity. So what about our initial hypothesis? Yes, the methylome could allow to discard some of the association due to reverse causality. And yes, in mediation situation, it could have a higher specificity than XWAT. And this was shown by both our simulation and our small theoretical analysis. I won't spend time on the strengths and the limits of the simulation, but the thing which is important is that we did a multi-layer simulation with realistic data and especially with different causal structures. And we also reached some low variability, which are more realistic. I'm sad because the method did not detect anything for the low variability, but it's more realistic. And we have lots of limits, of course. We did not consider all causal structure. We assume a linear relationship. We assume that all the effects were analytical within a layer. And because it was difficult to read the same order of variability between the different causal structures, we were not able to compare the structures, the different structures within. We did not simulate any confounders, and we could have made vary other parameters, such as, for example, sample size. So my last slide in practice, and this is a bit the take-home message. First thing is that all methods of design and analysis, postulate an underlying causal structures. But as soon as you work on the exposome on a high-dimensional layer, the underlying causal structure is often partially unknown. So this is important to know what you should expect for your method if the causal associations are not met for link design. This is really important. Second thing, the usefulness of interacting with data strongly depends on the non-causal structures. If you have a strong a priori of the causal structure, for example, you really expect mediation, in this case, it's better to choose the best method under the setting. But if do not have any strong a priori, again, it's often the case with the high-dimensional layer, it's better to choose a more robust, more conservative method, and we show that within the middle is robust, at least more than other methods. And last point, we showed both in our archive study and in our simulation study that the preliminary informed dimensional reduction using additional information, for example, using another biological layer, is useful to increase specificity. And now in epidemiology, we have lots of intermediate layers, a lot of intermediate biological data. So let's go. We should use them not only to understand biological mechanism, but also to try to do informed dimensional reduction of the exposome. So thank you. Maybe I was a bit long.